Hey guys, it's another beautiful day for another beautiful lesson. So far we've talked about circles and arcs in circles and angles in circles, and I know you are all wondering, when are we going to talk about polygons in circles? And for those of you that were wondering, today's the day. So that's pretty exciting for us. We're going to talk about polygons inscribed and circumscribed in polygons. So a couple of definitions. Take a look at the definitions for inscribed polygon and circumscribed polygon. Pause, read, hit play. So you just read about inscribed polygons and circumscribed polygons. Inscribed, when you say inscribed, you mean it's inside. When you say circumscribed, you mean it's outside, okay? So like if you think about circumference, it's the distance around a circle or on the outside of a circle. If you think about, for me, I just think of the word circumvent, okay? We're talking about prefixes. Circumvent is to kind of like avoid something or to go around saying something. So that means like outside, right? So you can reference things in two ways. If I look at the image that we have over here on the left-hand side, I could say that triangle ABC is inscribed in circle O because the polygon is inside of the circle. I could also say that circle O is circumscribed about triangle ABC because the circle is on the outside. So the circle is circumscribed about, okay? So you have to be careful because you can either say circumscribed or inscribed based on which you're referencing, the circle or the polygon. All right. So now we can talk about centers. If the circle is the thing that is on the outside, so if the polygon is inscribed in the circle, then it is called a circumcenter because the circle is outside. If the circle is on the inside, then the center is the in-center. Okay. So again, circles on the outside, the center is the circumcenter, circles on the inside. The center is the in-center, okay? We talk a lot about quadrilaterals that are inscribed in circles and kind of relationships that they have. If a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. This should make sense. If I look at this, angle B is an inscribed angle, right? Which means that it would be half of this arc AC. It's half of that, okay? And then opposite from angle B, right? The opposite angle from angle B is angle D. And that intercepts arc ABC going the other way, okay? And it's half of that. So if we look, those two arcs make up the full circle, which would be a full 360. But since they're inscribed angles, they're both cut in half. So their sum has to be 180. So if I look at my practice problem 1, not drawn to scale, let's say I know that angle A is 54 degrees. And I know that angle B is 62 degrees. I can figure out the other angle measures because I know that, so angle A goes with angle C. Those are opposites. So angle C, the measure of angle C, is equal to 180 minus 54, which would be 626 degrees. 126? 126, right? Yeah, okay. Then I also know that angle B is, it did not change my color. Angle B is opposite from angle D, so that means that measure of angle D would be equal to 180 degrees minus 62 degrees, which would give me 18 degrees. 118. Sorry, guys. Okay, so know that opposite angles in quadrilaterals that are inscribed in a circle are always going to be supplementary. Okay? So next, try this at home. Draw a circle. Draw a parallelogram inscribed in the circle. So you're drawing the parallelogram inside there with all of the vertices on the circle. I want you to pause right now and actually try this. Okay, so now hopefully you've tried that at home, and you may be having some problems. So if I try to draw, okay, so I'm just going to draw, well, let's see here. Actually, let's just draw two lines that are, I'm going to try to make them approximately parallel. That's not parallel. Okay, so I got these lines to be parallel. So the next thing that I want to do is I want to make a parallelogram. So if I make a parallelogram kind of like how I usually do, I would draw it kind of something like this. Okay, well then I would have something kind of like this over here. So you see the problem with that is that all of the vertices aren't on the circle, just the top two are. So let's see here, maybe I could try, so if I actually try taking this, well, if I connect this to 2 points on the circle, okay, that's pretty good. Okay, that's all right, that's pretty good right there. What do you notice about that shape? What shape would it have to be? Well, this would actually have to be a rectangle. You can't have kind of a parallelogram that's kind of flattened out, right? When you picture a parallelogram, generally you picture kind of like a slanted rectangle. A rectangle is a parallelogram, and if you are going to inscribe a parallelogram in a circle, it has to be a rectangle. So that's actually my next theorem. If I scroll down here, if a parallelogram is inscribed in a circle, then it must be a rectangle. All right. So based on this, there are some further conclusions that I can draw. First of all, if I draw in a if I've got my quadrilateral inscribed into a circle, then I know that it's a rectangle. And based on that, I know that BD and AC both have to be diameters. Well, how do I know that? I know that these are all right angles. And if that's a right angle, then the arc it intercepts has to be double that. So this would be 180 degrees. See, it's 180 degrees, which means that it's half of the circle. So I created a semicircle. So I know that if I have a parallelogram inscribed in a circle, then that parallelogram is a rectangle, and its diagonals are diameters. I know that O is the center of the circle, and I know that all of those portions of diameter, so like OA, OD, OB, OC in the diagram, those are all radii. And I can say AB squared, so this side length right here, this side length right here, squared plus AD squared, so this length right here, is equal to, or AD squared, is equal to BD squared. How do I know this? Well, I've created a right angle because it is a rectangle. So I can say that, and I can go through. I've got a bunch of different right triangles that are created, so I can use that with all of the iterations thereof. Okay? So let's do another practice problem. Let's say I know that measure of arc AB is 74 degrees, and I know that measure of arc BC is 106 degrees. I know that AB is 6 units long, and I know that BC is 8 units long, and I want to find the area of circle E. Well, if I think about it, 74 plus 106 is 180, right? So if that's 180, then I know that this missing portion of the circle is also 180 degrees, which means that I have a right angle down here. Okay, so that's 90 degrees. So if I connect AC, I know that that's actually going to be a diameter of the circle, and I know that I have now a right triangle, which means that I can use Pythagorean theorem or special right triangle relationships, it's a Pythagorean triple, to find the length of AC. So AC is 10 units long. 6 squared plus 8 squared is 100. Square root gives me 10. Well, that's my diameter. So if my diameter is equal to 10, then I know that my radius is equal to half of that, which is 5. So to find the area of circle E, this is a bit of a throwback, but you guys know how to find area of circles. The area is equal to pi r squared. Area equals pi r squared, which is equal to pi times 5 squared, which is 25 pi. And I know that some of you like to write that in decimal form. So 25 times pi is equal to 78.54 square units. All right, that's it for today. If you have any questions, feel free to send us an email. Feel free to let us know anything that you're struggling with. If you need more videos, if you need one-on-one chats, let me know. If you just have a super cool quarantine theme song that you've been listening to, feel free to comment that. But I hope you guys are all doing well, hanging in there, and yeah, have a great rest of your day. Thanks, guys.